So here's an example. I think I put this example up my very first term teaching first year. And I don't know if you knew, they did very badly that first year. You know, I don't know if you guys know this, I have an art picture. I've done it since my very first year. And that first year, people were hanging themselves, hanging me, blood and guts, right? So it gave you some sense of what was going on. All right, so here's a little program that we want to know what it does, right? And if you tried to trace it out, you would die, right? So instead, we're going to do it kind of more one step at a time and see what we can get out of it, all right? So if the input, right, the input here is an integer, and what does it print out? It prints out x's and y's and a's and b's and c's, right? So if n is 1, we print out an x. If n is 2, we print out a y, all right? So now let's trust this. Everybody trust this? We're going to remember this, and we're never going to go back and rehash it, right? So if we want to know what 3 does, well, 3 prints A, B, C, and it puts something in between. And here it prints out 1 less, which is 2, which is a y, and here 2 less, which is a 1, which is x, right? So you can just plug that in, right? So that's what 3 is. So we can ask what 4 is. Well, it's A, B, C. Well, here we plug in this, right? And here we plug in this, right? So you get that. And then 5, you plug in the previous one and the previous one, right? And then it grows, right? In fact, if you ignore the A, B's, and C's, and you just look at the X, Y's, and Z's, anybody know how long this is going to be? Fibonacci numbers, right? Because each one is the sum of the previous 2, right? So you get Fibonacci numbers to the extent that matters. So what's our running time, right? So, right, here's the recurrence relation. Can we solve this recurrence relation? First off, can we solve it? And the second off, there's something missing in it, so it's not even well defined. Anybody see what's missing? Yeah. You don't actually say 2, right? So you have to bring the 2 in there. All right? And yeah.
So for your algorithm here, in order for it to halt, like you know the base case for it to halt, n has to be equal to 0 or less than 0.
1 or 2, yeah.
Oh, so the base case isn't the first if statement. It's like the. I was just wondering.
Yeah, I don't know why I have this extra guy in there. I guess because I was trying to emphasize. I don't know why I had that in there. I haven't looked at it in 20 years.
Maybe just to avoid negative numbers.
Yeah. But I guess you're right, because here, if n is 0, right, you don't want to deal with, right, you're not going to do anything if it's negative. Yeah. All right.
You wouldn't get there anyway.
You wouldn't do this?
Like,
if they're negative, it's going to, this saves us from negative numbers.
Okay, it's kind of like a precondition kind.
Yeah. I think if I was doing it now, I might do it slightly different. I might say, if it's negative, do nothing, and if it's, right, but I don't know. I wrote this a long time ago. All right, so now we have to solve this, and again, the hand waving, right? You might notice, well, the first thing I said is you could ignore this, and then you can see it's Fibonacci numbers, right? And then you have to solve Fibonacci numbers. Or here I'm saying, well, let's ignore the fact that this is a -2, and and ignore the 3, right? And you suddenly get powers of 2. Right? Everybody kind of buy that? No? No?
So it's exponential?
It's exponential, right? Because, do I say that here? Here, if t, this is something you should know, is t of n minus 1, this should just scream exponential to you, right? Because I have 2 friends, and they have 2 friends, and they have 2 friends, right? We can say, what is the depth of the tree, right? The depth of the tree is order n. Whether we're doing this or we're doing this, right? The depth is order n. And it's pretty full. And you have 2 friends, so the number of base cases is going to be 2 to the height.
So why is it not order log n, the depth of the tree?
Because n gets smaller by 1 each time.
Instead of dividing it.
We're not dividing, yeah.
Okay.
Right?
Yeah, I think people,
Because I have 2 friends.
like think of t of n as then 2 of t of n. Or
That was the approximation, right? The point is that they're both, I'm going to claim here that every path, the length of every path is order n, right? Because given a path, sometimes I'm subtracting 1 and sometimes I'm subtracting 2, right? So in fact, if we can say what the tree actually looks like, it's going to kind of look like this, where this is, or actually the other way around, right? Let's do it this way, right? Here is if you subtract 2 each time, and here you subtract 1 each time, right? So this distance is n, and this distance is n over 2, right?
But if you had 3 friends, would it be 3 to the power?
3 to the, yeah.
I still don't get why 2t n minus 1 becomes 2n.
yeah. Why exponential?
Why the 2 here?
Yeah. Why do you add those two tables then?
Why exponential?
Well, so let's first see why what this guy does, right? This is every path is of height n, right? Because it's n minus 1. Everybody at this level is n minus I. In fact, I have a slide which is going to do this, right? This was just a warm up here, but right. So every path is of length n. So the number of nodes is 2 to the n. Right? It's a binary tree, right? We're going to do this again later.